All right. And so now what we can go in and we want to talk about is about vector addition. Okay. And so what we can get is that vectors can be added graphically. They can be added analytically. Or if you wish, numeric. Okay. And so when we talk about doing a graphic vector addition technique, there are multiple techniques that we could use, but we're gonna have a preference for certain ones in this, in this particular class. And the ones that we generally prefer are the ones that, extend to, you know, increase the number of vectors that are being added at one time and to not be limited in terms of how many dimensions you need to do your vector addition in general. So if we go and we take a look at our graphic method for adding vectors, then the technique we're going to favor is called the tip to tail technique. Okay. And so in this particular technique, what will happen is you are going to go in, we're going to draw, because it's graphic, the next vector to be added. Such that the tail of that vector placed at the tip of the previous vector. And we go in and we repeat this process until, all the vectors we're going to add have been used. Okay. Once we put all of the tails of the next vector at the tips of the previous vectors, and we put them all in terms of the ones that are going to be added up for this particular technique, then the sum for the resultant vector will go, and it's going to go from the tail of the very first vector to the tip of the very last vector. Okay. And that's probably the difficult part of the tip to tail technique, is that when we look at our resultant, we go, from the tail to the tip. So it goes tail to tip on the last one, not tip to tail. Okay. So it's easy to get it backwards, but with some practice, you won't, type of things. All right. So let's talk about how to do this graphic technique. Okay. And so if I draw in two vectors, vector A and vector B, and I want to calculate my resultant to be A plus B. So do R for the resultant vector is A plus B. Then what we do is we go and we draw out A first, okay? We draw A first, and we place the tail of B at the tip of A. Again, we can do this because, we can move the vectors. So these are placed, tip to tail. And then our resultant vector goes from where we originally started to where we finally ended. So there we go. That's our resultant vector. So this will be A plus B. Okay. Now, one thing we should probably note is that this is likely, if you learned how to do vector addition in trig or pre-calculus, then this is likely not the technique that they used in that situation. So we should at least make a mention about that. Okay. And so what we're going to make a note on is the parallelogram technique. Okay. And so the way that technique goes is we're going to draw in our, vector A, and we'll draw in our vector B. Now, the big difference here is that we're going to place them tail to tail instead of tip to tail. And then we're going to view that these form the two sides of a parallelogram. Okay, so there's our parallelogram. And then what you get is that the resultant is the diagonal of the parallelogram. Now, the problem with it is that there are actually two diagonals in the parallelogram. But the diagonal they mean is this one. Like so. Okay. So that's the resultant. And so it's very easy to end up with the other diagonal. And depending upon how you point it, it's either A minus B or it's B minus A kind of things. So there's an easy mistake on that part. But we can see that if we were to take vector B and slide it up here, because we're allowed to move the vectors, then this gives us that this would be, A plus B. Or if we were to take A and slide it over here, then that's B and then A, so that's B plus A, like so. And so technically, what we can see from this diagram is that our vector A plus vector B is equal to vector B plus vector A. And so this is one of those nice math properties. Anybody happen to know what this one's called?
Commutative.
Yeah, this is commutative. So what that means is that vector addition is commutative. It doesn't matter what order you add the vectors, you get the same thing. And so that's a really nice thing you get out of the parallelogram technique. But that's about it. Because the limitations of the parallelogram technique are, one, you can only add 2 vectors at a time. Okay. Whereas the tip-to-tail technique, you can add as many vectors as you want at a time. I mean, so we could picture that we're going to do vector A, and then B, and then C, and then D, and then E, and then F, and then G, and then H. And I want to go, what's my resultant? And the resultant's going to go from, since these are all aligned, tip to tail, 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 then the resultant goes from where we started to where we ended. And there it is. However, you're going to do parallelograms. You pick 2 vectors, make a parallelogram, find the diagonal, and then take that with the next vector and make a parallelogram and find a diagonal. And then take that with the next one and find a diagonal. You know, at some point in time, I will break you of that. I just got to give you enough to add, and you won't ever want to do that again. So, the other thing that's a little bit of an issue is that what's a parallelogram look like in 1D? What about 3D? You're like, yeah. Whereas the tip to tail, as long as we can draw it, we can do it in as many dimensions as we care to do. And we can add as many at one time as we wish to do. So technically, in addition to having vector addition being commutative, it is also associative. But I'm not going to demo that particular one. Okay. Questions?